Today we solve quadratic inequalities, which are much like solving regular quadratic equalities, where we set aside equal to 0 and then factor. Now if we look at this example, it's already set up in a format that is basically got our quadratic isolated to one side of the equation, greater than or equal to 0. If we take and factor that, we get x minus 4, x plus 3 is greater than or equal to 0. So if we were to solve this, if this were just an equality, we would say, all right, well, x would have to equal 4 and x would have to equal negative 3. These act as what are called critical numbers. And the reason why they call them critical numbers is because special things happen here. Looking at an actual quadratic or a parabola, we know that these are also x-intercepts. So we'd have like an x-intercept at negative 3 and 4, and I know that since my a term is positive, this parabola is going to go up. Now I can solve this inequality just by looking at the graph. The graph asks me where in fact does this graph or this quadratic happen to be greater than or equal to 0. In other words, where is it above that x-axis? Well, I can look at the graph and state that pretty easily. I can say, well, when this graph is less than negative 3, or from negative infinity to negative 3, in union with, because it also happens over here, from 4 to infinity. Now, if we're going to actually algebraically do this, what we want to do is we want to list our critical numbers on a number line. So here we have negative 3 and 4, and we want to test areas or numbers outside the lowest bound, in the middle of the two critical numbers, and outside the highest bound, and see whether my solution values are greater than or less than 0. So what I'm going to do is test f of negative 4, f of 0, and f of 5. And when I say f of, I'm talking about plugging it into this function up here. Now, rather than plugging in and finding the exact numerical value, I'm only concerned whether I have a positive or a negative value, because all I want to know is if it's greater than or less than 0. So when I plug in negative 4 to this function, I'm actually going to plug into the factored function. Plugging negative 4 into this first term gets me a negative number. Into the second term gives me a negative number, and two negatives multiplied together end up being a positive. When I plug in 0, I get a negative number followed by a positive number, and multiplied together that's a negative number. When I plug 5 in to this first term, I get a positive number followed by another positive number and a positive output. So you can see here that the numbers greater than or equal to 0 lie in this region and this region, which just happens to match what we found in the graph. I'm going to most likely have you do a lot of these algebraically, because we're going to move from quadratics, which we know what they look like, to polynomials, which we may not know what they look like, and test those. But you can also back yourself up by using the graph. So in this case, once again, our answer is all the numbers from negative infinity to negative 3 in union with 4 to infinity. So let's do another one. So in this case, my quadratic is not set equal to 0, and I want to take and do that. So I'm going to bring my 6x squared over to the other side, just because I like keeping my squared terms positive. So I have 6x squared plus 17x plus 5 is less than or equal to 0. So also in this case, we have a quadratic that's less than or equal to 0. So in order to factor this, let's just use the 5-step method for practice. You've got x squared plus 17x plus 30 less than or equal to 0. Factor that, what multiplies the 30 and adds the 17, that's going to be 15 and 2, both plus. Divide by the 6, reduce fractions, so this goes to 5 over 2, this being 1/3, less than or equal to 0. Denominator goes forward, so that's 2x plus 5, 3x plus 1, less than or equal to 0. Critical numbers, pretend like they were set equal to 0, so I have negative 5 over 2 and negative 1/3. And these are critical numbers. Basically, they're x-intercepts. So again, I would take a look at a graph, plot negative 1/3, which is somewhere around here, plot negative 5/2, which is somewhere around here, draw my graph, and again, this graph moves up in this case, just like it did before. I want to find out where the graph is actually negative or where it's below 0, which is over here. So from the graph, I can state, well, that's just between these two values, so it's from negative 5/2 to negative 1/3, which should be my solution, but I'm going to verify that algebraically. So once again, I'll take and put my critical numbers, negative 5/2, negative 1/3 on a number line. I'll look at values outside the two critical points and between the two critical points. F of negative 4, let's say. F of 0, I can't go 0 this time, so let's go f of negative 1, and then f of 0 out here. And we'll plug in, find some values. Notice I'm going to plug in once again to this function over here. When I plug negative 4 in, that's a negative number. When I plug negative 4 into this, we also get a negative number, which ends up being positive. Plug a negative 1 in, I get a positive, and a negative 1 in, I get a negative, which ends up being negative. And then finally plugging 0 in, I get a positive and a positive, which is a positive. In this case, though, I'm looking for values that are less than 0 or negative. So here is my solution. This is where it lies. And you'll notice that's in between the two numbers. So if we state that in interval notation, it's going to look exactly like this. So here's a word problem. Why don't you pause this, take a minute to read it, and then we'll go through it. So you'll notice that in this case, we have a set of axes here. And what this equation is describing is the height of the water relative to this arc. And the base of the arc is down here, the vertex up here. So they want us to write an equation that approximates the possible water levels below the parabolic arc. Okay? And once again, they're talking about a level of 0 here. So what we're asked to do is write an inequality, basically. Now I know that I can use f of x, g of x, doesn't matter. But we want to know when y is greater than or equal to, because the water would be rising above the arc, negative 0.03x squared plus 0.84x minus 0.08. And that's going to tell me when this water starts rising above the base of the arc. Now, they want to know, let's see, in part B, they want to say the water level is at most 0.2 meters high. That means this line going across has a distance of 0.2 meters up that arc, if you will. So we want to know when this graph is above 0.2. And they want us to go ahead and solve that. But to do that, I think we're going to use our calculator. So why don't you get that out as I'm continuing to write this and start plugging in the formula. So let's do that. So here's the equation. And let's take a look at the window that I used. So we're all on the same page. I went from negative 10 to 30 because I got a feeling this is going to be pretty wide. And I'll still go from negative 10 to 10. Let's see what happens. And we'll graph this. And you'll notice that my entire picture fits in the window. So this is mimicking the picture over on the left. And what I'm also going to do is, since I want to solve this, I'm going to pop in a y equals 0.2 for a second equation, because I'm going to look to find the intercepts. That's going to get me my critical numbers. Then I'll graph that again. Now you'll see that's really difficult to go ahead and view. So I'm going to blow this up a little bit, all right, in a zoom box. So I'll do the following. Or actually, let's not. Let's do this. Let's make our window a little taller. We don't need to see all that negative stuff. So we'll go window, and we'll go from -1 to, let's go, I want to see that gap a little more. Let's just go to 4. And it's going to cut off the maximum part of this graph, but I'm going to be able to see the 0.2 a little bit better. So there's my 0.2. So I can see now that it's 0.2 up that arch. And I want to find out where are these important numbers. So we're going to take and calculate an intersection, 5. And I want that blinking piece to show up somewhere. And it looks like it's right there, so I'm going to hit enter 3 times. And that's going to happen at roughly, well, maybe it's not going to happen. Let's try it again. Intersect. 1, 2, 3. At 27.66. And then let's find the other side. And we've got second calculate intersect. And we're going to move all the way over. It'll take a second to get there. There it is. I'm going to hit enter 3 times. And 0.33. 0.34, let's say. So these are my critical numbers. And we notice the graph looked like this, and we're above here. So once again, if those are my critical numbers, and where is this greater, it's in between that interval. All right. So to solve that inequality, we want to know when is it at most 2 meters high between these 2 points. So we could say, well, when the x value is at 0.34 and 27.66, it's 2 meters high, and they want to know the width of the river under the arch when that time happens. To find that width, well, basically we're just taking and subtracting these 2 x values. So if I take, this is part B, part C, if I just take 27.66 and subtract off 0.34, I'm going to get my answer. So 27.66 minus 0.34 gives us a width of 27.32. Is that meters? I want to say meters, yes. All right, and that's all we've got. So moral of the story, set aside equal to 0, find your critical numbers, do your testing between the intercepts, and then state the answer. Go to my math lab, get the problems done, and we'll see you tomorrow.